Good afternoon, everyone. Thank you so much for joining the call. We are very delighted to have you all present at the AI for Mineral Targeting Hack Information webinar, where we will be providing you a brief overview of the India AI mission, about the perspective of why we are doing the hackathon, addressing all your queries, and we also have expert insights from experts including Arun sir and Devkumar sir, who would be sharing a brief overview of why we are doing the hackathon and also the area that we have chosen, along with brief detailing on what mineral prospectivity modeling from an AI ML perspective means. Arun sir, could I please share my presentation?
Yeah, I have shared the presentation. Is it visible?
Yes, I would like to share my screen and then walk the participants through the India AI mission.
Yeah, sure. Okay, I'll stop sharing.
Right. So India AI Mission is a Government of India initiative launched on 7th of March of 2024 to democratize and catalyze the AI innovation ecosystem in the country. The program objectives include creating large-scale social transformation, leveraging the power of AI ML, and with a particular focus on sectors of social importance, including healthcare, agriculture, critical minerals. The initiative aims to enable the access of all foundational resources, including data sets, models, compute, scaling infrastructure, which are critical for AI innovation, through ensuring that the responsible and ethical innovation is promoted for India and within the world. The idea is to get India ready with its workforce at the forefront, creating and innovating through these innovation challenges and hackathons, leveraging the power of AI for social transformation. Across the 7 pillars, the National India AI Mission is enabling the creation of this ecosystem through which we can address a national level scale transformation. Within the India AI compute capacity pillar, the idea is to provide access to modern hyperscale AI compute infrastructure as a service. Within India AI Innovation Center, the aim is to provide the development and deployment of indigenous large multimodal models and domain specific foundational models. Within India AI Datasets platform or AlKosh, the aim is to provide streamlined access to quality non-personal data sets to catalyze data-driven governance and innovation. Through India AI Applications Development Initiative, the aim is to develop and scale and promote the adoption of impactful AI solutions across critical sectors. Uh, Through Future Skills, the aim and the objective is to promote AI in BTech, MTech, PhD, and postdoc programs and set up data and AI labs in Tier 2, Tier 3 cities. Through India AI Startup Financing, India AI Mission is supporting and accelerating deep tech AI startups and providing them streamlined access to funding for futuristic AI projects. And across the 6 pillars, safe and trusted AI is enabling the development of tools and frameworks for self assessment and ensuring that the governance infrastructure underlining the 6 pillars is as robust as possible. In particular, India AI Applications Development Initiative seeks to promote the development, deployment, and scaling up of impactful AI solutions across critical sectors. The aim is to enable AI for social good by supporting the development and scaling up of citizen-centric AI solutions that have a potential of catalyzing large-scale socioeconomic impact. The aim is to make AI for India in India by harnessing the high quality data sets, local talent, indigenous foundational models for AI innovation, which are contextualized to India's unique challenges and opportunities. The objective is to enable population level scale up by providing resources, mentorship, coordination support for enabling the winning solutions to be scaled up for national level deployment. And throughout this, as I mentioned in the previous slide also, the the focus is to promote responsible innovation by engaging with the broader innovation ecosystem, including startups, researchers, industry, students, among others, for developing AI solutions that are catered to India's needs. The other pillar that we are going to be focusing today on is India AI Datasets platform, AIKosh. It's a hub for all AI resources, datasets, models, use case libraries, tools, development environment, which is functioning as an access layer for India AI, catalyzing AI development. As of now, we have AI ready datasets and models available on the platform. But through the course of the next couple of months, we will have compute tools, sandbox environment, and community also available on the platform so that all those who are contributing data sets to the platform, including government and non-government individuals and enterprises, are able to bring together providers and users of data sets, models, and compute so that users, including startups, researchers, academia, government, can actually benefit from the availability of the large scale data sets that India currently has. In particular, this initiative actually marries the two pillars, which is India AI Datasets Platform and India AI Applications Development pillar. Through the hackathon, we have partnered with Geological Survey of India under Ministry of Mines to enhance mineral discovery and geological analysis using AI, particularly in Karnataka and Andhra Pradesh. Through the expert presentations, we will also be focusing on why we have specifically chosen Karnataka and Andhra Pradesh. Uh, Going back to the slide, the data sets are available via AIKosh, which include geoscience data sets in examples including geological maps, mineral exploration blocks, etc. A total of 12 data sets are available on AIKosh, which are relevant to the GSI hackathon. Through them, the participants are requested to identify new potential areas for exploration of critical minerals like IEE, copper, and other commodities like diamond, iron, and gold, locate unrevealed and deep-seated mineralized bodies with depth modeling, develop AI ML models for data cleaning, integration, modeling, and validation, and generating mineral predictive maps showing exploration targets visualized through map sections, etc. Through this partnership, we are inviting industry, government agencies, students, startups, and research institutions to apply for the hackathon and submit their solutions. Each application will then be judged by a multidisciplinary jury composed of experts, including government stakeholders and technical leaders from the industry. As you may be aware, the deadline for submission was previously 12th of May, but we have basis the suggestions that we had received from the applicants, we have extended the deadline to 13th of June. The submissions under the hackathon will be assessed in two stages. One will be screening, second will be evaluation. And the assessment parameters include novelty of the proposed solution, ability to handle complex data sets, clarity and details in the report that we have requested from the applicants, and feasibility of implementing the solution. Awards include 10 lakh rupees for the first prize winner, 7 lakhs for the second prize, and 5 lakhs for the third prize. Special prize also includes of 5 lakh rupees for all women's team. Through the webinar, if you have any queries on the specificities of the application process, the eligibility criteria, including technical queries, we'll be happy to address them through the uh, chat box. We request you to please pose your question either on the question and a chat box or through the chat box that is available. We request Devkumar Bhattacharya sir to please inform the participants and share with the participants the value addition of the hackathon that we are running as of now.
Thank you, Antara, and welcome to all the participants who have joined. I find 54 of them. Welcome, Dr. Porwal, Dr. Arun, our esteemed panel of judges, India team. So as you are aware that Government of India is actually investing and promoting application of AI, ML, DL technologies into different parts of our say operations of our different sectors, so that this benefit of this new technology actually helps in growth of the country and benefiting the citizens. Now, when we talk about application of AI ML in different industries, there are a lot of success stories. But here today, and this particular hackathon is very specific, and it is for geoscience subject, and particularly it is the mineral prospecting. So here the importance is that in this field, uh, that revolution which is happening in other fields is not that way, is not that much significant at this point of time. That's why there is lot of gap, and there is lot of possibility in applying all these new technologies into this. As you know that Government of India has a critical mineral mission. Parliament has passed that, and then there is a lot of requirement of new set of minerals which are for various energy transition minerals, technology minerals, which are considered to be very vital in today's world. And now many of the countries, they have started using these different technologies in finding critical minerals and other minerals also, particularly in the which are concealed, because over the years, hundreds of years, people are exploring, exploiting mineral resources which are very easily uh, viewed and can be accessed over the surface. But now the time has come when this particular type of deposits, which are very near to surface or on the surface, is actually depleted, and now we have to find new areas at depth. We call it deep seated minerals or concealed minerals. Now, when we talk of geoscience data, GSI actually acquires a lot of baseline geoscience data, including geological, geochemical, geophysical data, along with other data sets. As Antara was conveying, that there are 12 data sets available. Now, the point is we have to use these data sets and use new AI technologies, where it has to be meaningfully analyzed and combined, integrated, to find target areas where further exploration can take place. As you know that in mineral exploration, there are different stages. We start with a very regional scale. We analyze regional data, then we actually reduce the area, then we go to some district scale, and then camp scale, and then deposit scale. So here the main scope will be the first prospecting of maybe 39,000 square kilometer area, from where we have to drill down to maybe 1,000 square kilometer area, or even less, depending upon the nature of data, nature of anomalies available, and the technology that you are using to integrate them. Now, it is very important that for whatever analysis is done, whatever interpretation is done, there has to be a geological rationale to that. We always expect that those who will be participating and submitting their models, it has to have some kind of geological significance and explainability. For example, you know that in geology, in recent times, mineral system approach is taken by various countries to locate new mineral systems, new mineral deposits, and these mineral systems has certain characters and reflection in the baseline data. I think later on, when our Professor Arun, Professor Porwal gives the presentation, we'll realize that that is a kind of approach that we were supposed to take. So we actually we expect to generate a lot of predictive maps for different commodities, because you know the mineral systems and the mineral deposits, there are depending upon the community, the geological setup, there are different kind of processes that generate the mineral deposits, and these processes are reflected also in our data set. So there has to be a 2D map, 2D predictive map, and also we expect that there should be a 3D block or sections, multiple sections, where the participants can pinpoint certain anomalous areas at a specific depth. So these are the main outputs, or based on which actually the judgment will be done. Apart from your rationality, how you are analyzing the data, and how much you are actually able to corroborate with the mineral system theories and the specific data. So I think with this, I'll stop, and I request Devjani to take over from here, and she will just state about the area and the mineral commodities that are available, where this hackathon, where from this hackathon data is taken. Thank you very much.
Thank you, sir. So, Antara, if you don't mind, can you please share the presentation on the area, geological part of the area? Am I audible, Antara?
Just sharing, ma'am. Just sharing, ma'am.
Yeah. So, a very good afternoon to one and all. So, like Devkumar sir was sharing that please provide us with some meaningful solutions. By that, perhaps what he meant was previously there have been solutions in the previous hackathon where people were trying to look for all the PGs and the nickels in the granitoids. So there lies a major problem. So while we analyze our data, it is very important to know the geology of the area, the lithology, and what all mineralization that can be associated with a particular lithology. So coming to the area that has been offered for this year's hackathon, we have, as elaborated earlier, some 39,000 square kilometers that is spread across the states of Karnataka and Andhra Pradesh. As shown in the map, and as it has also been provided to you in the documents that is uploaded at IndiaAI's web portal, that is dominantly this area exposes the Dharwar Craton, one of the ancient nuclei of the Archean times. The Dharwar Cratons, it is composed of number of schist belts, and if we look into it, we can see dominantly this Dharwar crater, it can be divided into broadly two parts based on a major northwest-southeast trending shear zone, that is the Chitradurga eastern margin shear zone. The western part of this shear zone, it is known as the western Dharwar Craton, and the eastern part of it, it is the eastern Dharwar Craton. The western Dharwar Craton, it is marked by much broader schist belts. Dominantly here, what are shown here in the map that we have provided, or the area that you will be working upon, it's the Chitradurga schist belt, this green part. Its age equivalent is the Shimoga schist belt, a little bit yellow that is shown here, and this little brown, it is the Baba Budan schist belt, that is the oldest of all these schist belts that is given for you to work out. The western Dharwar crater is actually more polymetallic in nature. It hosts gold, copper, little bit of silver, and some sporadic amounts of antimony here. So please look upon the reported mineralizations by GSI or even the old workings that I've given here. While you work out your solutions, it will lead you to a better finding of the deep-seated solutions that we are looking for, instead of randomly preparing some programs or running some programs to yield solutions that might be baseless. It won't be giving us any result, and perhaps it won't work out for you also. Now coming to the eastern part of the Dharwar Craton, that is the eastern Dharwar Cratons, it is relatively, eastern Dharwar Craton is considered newer than the western Dharwar Craton. It has a number of narrow schist belts, the Bellary Sandur schist belt, the Ramgiri Panchkarla schist belt, the Hongurt Kushtagi schist belt, and the Hatti Maski schist belt. This part is dominantly known for its auriferous deposits. Perhaps we all know about our Kolar deposit that is in this eastern Dharwar schist belt, somewhere in the southern part. So when you look for your models or prepare your models, perhaps gold would be a major point, major mineralization that we would be modeling for. The eastern Dharwar crater in this part of the area, it also the reports of kimberlite and some lamproids have been given. And so for during the modeling part, so dominantly we are looking for critical minerals, that is the Re, nickel, Pg, copper, the diamond, iron, manganese, gold, and associated something else if you can find. So now you know, based on the spread of the mineralizations that have been reported or the lithologies that host them, how and where to find them. So while preparing models, I'm again repeating, please take a look at the lithology, take a look at the mineralizations that you can find in those particular lithologies and prepare some meaningful models. I think I'll end it here so that Dr. Porwal and Dr. Arun can take it forward with what exact solutions they expect from the participants. Thank you, everyone. To you, Antara, please.
We request Arun sir to please make his presentation.
I hope I'm visible, and I'll just share my screen. Yeah, is my screen visible?
Yes, sir.
Thank you once again. Thank you for the kind invite and the opportunity. First of all, I'd like to thank Professor Alok Parwal for his inputs. Basically, I want to see that and more from a computer science background and a machine learning background. Last hackathon, we have seen many people using machine learning approaches. So I just want to talk about that perspective. With that context, I'll just go through the presentation. So we know that these are our, the data sources. So basically, right now, like ma'am has already explained, we have a variety of data sources of the data. So from this, this set of data, how are we going to take, this conclusion? So that's what, basically this, how are we going to model this mineral occurrences? So that is what is a problem before us. So, all of you are well aware of the mineral exploration workflow. So you have different sources of data. You have to pre-process the data. Now you will integrate this data together, and we will explore. We'll go with the exploration. So this is what basically we are doing. So this is how a proper mineral systems model will work. Traditional prospectivity analysis or the model. So basically what we used to do as a geologist, or maybe people used to do as a geologist, what they used to do is like they first prepare a model and then they give data to that model to get the output. So as domain experts, you'll be very familiar with this type of approach. But nowadays, with the advent of machine learning, so we give the data and output and we get the model. So that's what basically nowadays we are doing. So so why this is advantages is that, usually in this type of real world problems, so we don't have like, the problem is that the relation between this input and output is not very well constrained. So if it is well constrained, we can go with the traditional approaches of, you have a model, you give the data and you get the output. But provided it is not well constrained, it is something which is dynamic or which changes with the data, so then it is advisable to go for machine learning type of approaches. So why machine learning in mineral prospectivity modeling? Already we have discussed, like, because most of these geological processes are poorly constrained, and model selection is very difficult. So we have to actually adjust our model towards the data. So based on the data, we have to come up with a model. So that is where usually we do. So we have a set of data, and from those data we will derive a set of features. Then we have learning algorithms, and from those algorithms we will get the output. So this is what basically usually we do. So this machine learning simply involves optimization of parameters to make the best prediction. So that is what we usually do in a machine learning perspective. All of you may be aware of this. So we have the data. From that data, we'll extract out the features, and we'll predict the prospectivity at that place. So the idea is that from a machine learning perspective, or from a computer perspective, a computer sees everything in terms of features. So for example, in an apple, we see the apple as an apple from a human perspective, but the computer sees it as a point in a feature space where two features can be the shape and color, or color and weight. So based on that only we are perceiving this apple. So your algorithm always sees things as a point in a feature space. So this is an actual image, and the image is having say 2 bands, and we can see it as a point in that feature space. So this is the basic idea of a feature space. And so we have all these data, and we have the features, and we have the learning algorithm which will learn the relation between those features and the output. The output can be your mineral prospectivity, at a particular location. And also, so you have different types of data. The basic problem here is directly measured data, so it's fine, you have low uncertainty there. But for some data which is not directly measurable, which is interpreted from some measurements or observations, you always have high uncertainty. So whatever is the data, so usually we always say that the quality of your machine learning model. So here in machine learning model, you are giving data and you are trying to learn a model out of the data. So always the quality of the machine learning model depends on the quality of the data. So pre-processing parts are very important, very significant in this entire process. So you have machine learning algorithms. So you have different machine learning algorithms. In unsupervised case, you can go for clustering, because as a kids, when we get some fruits, we will just group them based on the color. So this is clustering. So same way, if someone gives you an apple and say that this is apple, again give another sample of apple and give that and say that this is also apple. So you slowly learns the features of apple and how to distinguish between apple and a non-apple. So this is what supervised way of machine learning says. So regression is also a part of supervised machine learning. So already we have, you may have seen the clustering techniques, like basically in that feature space only it also works. And based on that distribution of, those points in the feature space, it will group certain as one set of in one class or one cluster, other set as another class. So again, same way this classification algorithm, but classification algorithm is a supervised way of doing it. So what basically are we saying is that all these models, they will take input and they will predict some labels. So we are actually modeling, we are building a model from the data. So if it is a classification model, basically it's learning a decision surface which can classify the data maybe into one mineral occurrences to another mineral occurrences or some sort of this. So yeah, any of these, for example, if you take neural network, the neural network is learning these weights, but in a way, by learning the weights, it is adjusting this decision surface which can accurately distinguish the data. So we can use these approaches for regression and all other sorts of applications. So basically we are learning a model which can map your independent variables to a dependent variable. So this is a common workflow of a machine learning. So what we usually do is we extract out the features, we classify them, those objects based on those features. So you have input, you have output based on that. But there is something called we directly extract the features. So when we extract the features means now, like ma'am we discussed, you have a lot of data, but you may not be directly feeding this data to the model, but in place you will be extracting out some features from this data and you will be feeding on to this model. So that's what you are actually doing. So you have say your actual feature distribution, and now here you have it like it's more separable in a learned feature space. So this is like learn the representations of the data. So basically you have the feature engineering, you learn the representations from these input features. So here if you see the first figure, we are actually synthesizing the features. So basically we are extracting the features and we are giving those features to the learning algorithm. So that means from your actual data, you may extract out some features. For example, if it is an image, maybe it's having 400 bands. So you will extract out some bands and you will feed that to the model. But here, from the primary data in deep learning type of approaches, the system itself is learning the features. It's using those features to classify it. So this is how you encode the features, and based on those features only you are classifying it, whether what is the label. So if you see, this is a very simple example of a neural network. We can see that we are giving a spectra or some sort of a data, and it will just take it as a digital data and it will try to classify it. But in this manner here, we are learning in the subsequent layers, we are learning the features, and based on the features we are discriminating. I mean, we are deciding the label. So this is what basically we are going with all these machine learning models. So I mean, machine learning models, they usually use features, but when you go to deep learning features, we are learning the features and we are classifying it based on those features. But what are the problems? Our main problems is like our advantages is that we learn a better representation. When we learn new features, we are the machine itself is learning those features. The advantage is that we are learning those features from the data, so those features will be better than our actually extracted features. This is in most cases that we expect. But problem is that it's having too many parameters to optimize, and also we need a lot of training samples. So this, and also the effectiveness of the model actually depends on the effectiveness of this training samples. So what are the solutions? So one solution is that nowadays there are a lot of generative algorithms which can generate synthetic samples or fake data. So we can actually use those synthetic samples to train. So what we used to do is there are generative models or generative approaches. We will use those data and we will try to train our models using those data. But that actually mostly results in overfitting, because these data are also derived from the existing samples, so may not have that much variations, and that itself requires a lot of data. So one way is that we can use this unsupervised way of learning to get the intermediate features, and we do the classification or clustering in that feature space. It will be more clear here. So here we can see that we are using an autoencoder. So we are learning these samples, this feature representation from this autoencoder, and we are using those representation for, actually here you can see that I'm giving this input and I'm getting this input itself as the output. In that case, like we are using PCA and other things, here we are using an autoencoder to learn these feature representations. And basically, we are using those feature representations to classify or to do a regression. So instead of using the actual features, we are using the features learned by the network. So the idea is that we will learn the features, and those features will be used by a classifier to classify. So what are the features being learned? This is a big problem, because most of these deep learning models are black box models. You can actually see that here, this sharp values, you can see that these dotted lines represent the relevant features, but these red values, this denotes actually the sharp value given by your learned by your model. So the colors represent the features which are being given importance to by the model. I'll tell you a simple example. So if I take a model and if I train it for for classifying cats and dogs, and if I give black cats and white dogs, the moment I'll give a white cat, it will classify it as a dog, because it is taking color as a feature. So sometimes the machine may learn some features which are not required, not relevant. So those will make the model take wrong decisions. So explaining or reliability of the model is something very important. So we have to this is where we take it up. So these are the important features. This dotted line denotes the important characteristic features, and this colors denotes the. So that is also one way of estimating the accuracy of your model. So now now that we have understood that transition to a machine learning or a deep learning perspective, but always this requires a caution, because you have conventional models that already we have seen, where we use the data to get the models. But how are we bridging the gap between these models? Because if you ask any geologist or any person, mostly he will be more or less interested in this type of machine learning conventional models, because the machine learning models may not be very reliable. So how can you bridge the gap between? So this is what last time also during the hackathon, we have seen some solutions where people are blindly using ML models. So this is one of the main perspective that we should look into. Rather than blindly using these machine learning models, we should try to bridge the gap between the conventional models and ML models. And also we should be able to correlate this with the underlying process. So basically the physics based or the geological processes, we should be able to correlate it, whatever your machine is predicting, whether it is considering these physical processes. So we can have physics inspired models or learning underlying models. We need to train those models. So that domain information has to be incorporated into this machine learning model. This is very important, because sometimes simple decision trees can give you better, reliable results than complex deep learning models. So model selection is very important, and also ensuring quality of sample. So so the sample quality, how you can ensure it, how we can quantify it. So these are also very important aspect. And the pre-processing steps are very crucial, because mostly when we do blind pre-processing, sometimes we may be losing those, those features which are very important, and sometimes the weak features may be more important than the prominent features. So understanding what a model is learning is very important. So unboxing these black box models ensures reliability and generalizability, need to correlate with characteristic features. All these are some of the points that we need to understand when we go for these ML models. And all these samples needs to be correlated with the ML models. So another part is like when you say you are classifying something, you have got a sample. That means you got a matrix of different data. You are stacking one data on top of other. So when you are making a prediction or when you are regressing it, so are you considering the characteristic features? So this requires, because there will be a lot of variability, are you considering all those variabilities? If there is a multiple sensors or multiple modalities of data, if you are considering, where there's a proper correlation between those data. So these are all very important. And also we need to consider the metadata for training explainable or physics inspired models. To sum up, actually we have to have these prospectivity models to use to have these input features. So basically, instead of using handcrafted features, we can use machine learning features, but with the caution that we should understand what feature it is actually learning, and this way we can better supplement those models. So some case studies of recent ML applications. So one is like there are some models which you can also explore. So this is just a surface level explanation of some advancements which may be useful to the participants. Like one is like along with considering a so usually in machine learning models you will only consider the spectral context, or you'll only consider that data. But we can also consider the spatial context. There are some specific models for that. You have transformers, now you have capsule networks, or all these models can also consider the spatial context. So, and also the interpretation, or I already explained, you can use any of these explainability models to clearly understand what your model is learning, whether your model is actually learning something which is relevant to the to a common logical understanding that you are having about that particular mineral. So for that, you can use any explainability techniques like sharp, line, or maybe any other techniques you can use. So also spectral unmixing, there are a lot of approaches which are being used for spectral unmixing. So you actually go beyond a pixel level to unmix it. Nowadays, there are a lot of deep learning models also being used. This is a common strategy. Spectral unmixing basically means you are going beyond that. Here you can see some pixels. They are, because of the resolution limitation, most of the data which you are using because of the resolution limitation may not get pure pixels. And also in this case, in mineral case, it is a nonlinear mixture. So how to unmix it? So you can even use the nonlinearity of these autoencoders to unmix it. So, and also we can enhancing the data rather than just using a bilinear or bicubic type of interpolation. We can also go for some more meaningful or advanced or sensor related mechanisms, which even we can use deep learning or machine learning approaches for that. So but always we need to understand. So even for enhancing or all this pre-processing, one thing we have to always understand is that we need to understand what the machine is actually learning. This is very important, and we are not sacrificing the characteristic features. For example, the spectral fidelity is very important. And also while fusing also the different data, sometimes we may get, because in most of these cases whenever we have the data, sometimes we may not have a one-to-one correlation. So whether your model is expecting a one-to-one correlation, otherwise you can even use it as a prior to improve your multi-model decisions. And another important thing is, like for example, the context or the correlation between different aspects. We have to model it in a proper way, and for that also there are approaches like you can actually have this relationship modeling in an imagery context. So you can use a lot of data augmentation strategies using GAN. Augmentation already I discussed. You can generate fake data or synthetic data when data is not available. But we have to be aware that so if you are using a very small set of samples for generating this type of samples, so sometimes we'll just repeat. We'll get a repetition of those samples. It may not represent any variability, or sometimes it may be even learning a noise as a characteristic feature. So that part we may have to take care. And so that is where generative approaches, we can also use it for different pre-processing stages. But only thing is that most of these generative approaches are not like black box nonlinear models, so we should take care of while we are trying to use those models. And also now people are also coming with, we take a small analogy. We learn things in a supervised way. We also learn things in an unsupervised way. But you remember when we were kids, we also learned certain things in a self-supervised manner. Like when a guest is coming, if we are behaving good manners, we may get some perks, like so some rewards. So these rewards can be positive as well as negative. So based on the rewards, we will keep on learning certain things. So that means a self-supervised way of learning. So that means mostly in cases where the data is coming in, and when we can use this type of self-supervised way for improving our modeling and our results. So basically in dynamic environments, we can always use this, because most of the machine learning models or even your deep learning models are static models. Once you train them, you cannot update their weights. So we can also think of reinforcement learning as a way of reinforcing this. Those type of studies are also there. We can explore those type of studies for a better perspective. Also, one another perspective of this hackathon is, how are you using all these different modalities of data? See, you have some data in the form of PDFs, you have some reports from GSI. So can we use even the text mining, or you can get some more information from this diverse set of data? Because already there will be some reliable reports. So can we take that also as a prior? And so maximum data utilization. You can see a lot of literatures in this regard as well. So the basic idea of all this discussion is that we are looking for a solution which is reproducible. That means it will not work only for a particular area, or it should be reproducible, or should be scalable, and also it should be reliable approach. So that means the underlying processes should be very clear and should not be a very blind black box type of model. It should be interpretable. That means we should be able to interpret and explain the results. And scalable, of course, it should be scalable to a wide area and for other sort of minerals. And we should be able to incorporate the underlying processes and the data uncertainty, and also we should come up with some way of quantifying our accuracy, or at least saying that okay, this way it is reliable, or our solutions are reliable. So yeah, that's all from my side. Once again, I acknowledge our collaborators and contributors. So these are some of the references. Thank you once again. Once again, I thank Professor Porwal for the kind inputs, and also for GSI for the kind invite and the opportunity. Open to questions. Thank you.
Thank you so much, sir, for this enlightening presentation. I hope our participants also understood what various techniques that they can use and leverage to make their solutions as viable and feasible for GSI to adopt and scale. Could we also request the participants to share their queries on the chat box? We are responding to them in the meantime. If there are any other queries, we would also be willing to take them up. The webinar is scheduled to end in another 7 to 8 minutes. If there are any queries that you have, you may unmute yourself also and raise them. Our experts will be more happy to address those queries and get the solutions from you as best feasible way as possible.
See, on one query, I can see here is the evaluation metrics. So maybe you can use, it actually depends on the basic problem that we are dealing with. If it is classification, we can go for maybe a kappa type of accuracy measures, reference score or such things. If it's regression, we may have to go for, the metrics accordingly.
Okay, just a minute. I just looked at this question. What is the effective way of combining the geospatial data sets? The most important thing here is not to worry a lot about the algorithms. You have to focus more on whether these geospatial data sets are representing the mineralization processes. So you start with the mineral system models first, and then figure out which are the predictor maps, which are the GIS layers that would be best capturing the mineralization processes. So once you have the mineralization processes captured properly in different data sets, and remember, the most important data sets are going to be the geological data sets. It's going to be your structures, your lithological maps, your geochemistry, to some extent geophysical, but not to that large extent, and remote sensing not to a large extent, because you are looking at something which is deeply eroded, highly undercover. So it's Dhava Craton. You wouldn't get that many exposures there. So if you don't get exposures, you can't do a lot with remote sensing. So the kind of data sets that you are going to use, they have to be relatable to the geology of the ground. And that's why try and focus more on geochemical data sets, geological data sets, structures, grade of metamorphism, lithology, and then try to convert them into some kind of maps that can capture the mineralization processes. So if you're looking at, say, for example, gold, and this is orogenic gold setting. So in orogenic gold setting, what kind of processes are involved and how you can capture them. So once you have your geospatial data sets ready, then how you combine them doesn't matter a lot, as long as the result you are getting is geologically meaningful. So at the end of the day, we want a mineral deposit. That is what we are looking for. So if you can get it using a random forest, or you get it using a simple fuzzy overlay, or you get them using CNNs or GANs or whatever, it doesn't matter a lot, as long as at the end of the day, you find a mineral deposit. And always remember Occam's razor, the simplest models are the best models. I think this question, Dr. Bhattacharya can answer better. Will there be opportunities for selected teams to continue working? Dr. Bhattacharya? I think he's not available.
Sir has gotten busy with something, sir. So regarding the continuity of personnel who would be giving us proper solutions, GSI would be contemplating on what will be done with them, but the best of the solutions would be appreciated, and maybe a token of appreciation would be given. That's it from our part.
Alok sir, could you take this question? There's one question on depth modeling. The participant is asking
yeah, that's a good question. Depth modeling. So essentially, I would suggest starting with a geophysical inversion model or a forward model. Doesn't matter. You can use forward modeling or inversion modeling, but start with a geophysical data set. It could be gravity are easier to. Yes, gravity would be easier to use for inversion modeling or even forward modeling. Magnetics becomes a little bit more complicated, but you do get some good results. So yes, start with the geophysical data and then populate geophysical data, do a model, a 3D model, you can use the GeoModeler, for example, or GoCAD. But start with the geophysical data set, generate an approximate Earth model of the in 3-dimensional, and then populate it with geochemical data. You have got surface geochemical data, and that surface geochemical data has to be projected downwards. If you have some drilling information, you can use that to populate your model, and then try and model the mineral system. What would be the possible pathways, and what would be the possible traps within that model. So yes, start with geophysics and then add geological and geochemical information to that. Please take about, okay, raster, aster data set. Have a look at aster data set, because you can capture a lot of alteration using aster. But this area would not have very strong exposures. So if you don't have exposure, you got soil on the top, then most of aster would be picking up clay signatures, which may or may not be relatable to mineralization, hydrothermal alteration there directly. So just be careful with remote sensing data. I suppose geophysics would work much better there. Now, PDF and the text mining. Text mining is, we can do a lot with the text mining, but to begin with, it would be maybe going through an archive of literature, maybe published papers, as well as the technical report of GSI. So can you write a software that can search through an archive and then bring out the relevant publications? And within that relevant publications, can you locate specific paragraphs which are of interest to you in terms of whatever exploration work has been done there? So this would be something like developing a Google kind of search, but focused on geological information. And your search area would be the technical reports of GSI. So this is what, at this stage, we would expect from text mining, although you can do a lot. And there's a lot of work going on currently, but you can do a lot more, including trying to develop mineral systems models using text mining, but this is far too complicated. Can I use the same methodology? Yes, you can. You can. There's no one will stop you from using LLMs on GSI technical reports.
So there's a question by Sankar. He wants to
Yeah.
understand if he can use the same methodology of his personal paper that he's working on for mineral exploration. The dataset area and minerals will be different, but methodology of processing data will be same, or pre-processing the model will be the same. And after submitting the solution here, can he submit the paper then?
I think there's going to be some IP issues involved there. I would strongly advise you to contact IndiaAI regarding this. What are the IP issues involved there? As far as using the methodology, I mean, there are also standard set of methods that we use for prospectivity modeling and exploration targeting, all these AI and ML methods. And again, let me tell you, it's not just, this hackathon is not about developing ML or AI algorithm. It is about identifying exploration targets, and you're using AI and ML as tool. So yes, you can use established methodology, established algorithms. If you develop your own algorithm, which is more relevant to geospatial data set and geological exploration data sets, perfect. We'll be very happy to look at that, because most of these algorithms have been developed for other domains, so computer vision and identification of cats and dogs and all those things. Geology is very different, and the geological problems and mineralization problems are entirely different. So if you can develop an algorithm that is specific for mineral exploration, that would be perfect. We would be looking for it. But yes, you can use methodologies that are already available.
Noted, sir. We don't have any other queries that have been left unanswered. We thank you very much for your support in answering the queries that the participants had raised. And we also, GSI team and India AI team together, thank the participants for joining the call and for so proactively getting your queries addressed on your applications. We look forward to reviewing it and getting back to you with a positive response soon. Thank you so much for your time. And if you have any other queries, you may reach out to us on the email IDs provided by my team, fellow3.gpi-indiaai@meti.gov.in or sudhir.reddy@meti.gov.in with the subject line queries for IndiaAI Hackathon on mineral targeting. We'd be more than happy to assist you with your queries as in when we receive them. And we'll also share it with the technical experts to provide their inputs on them. Thank you so much for your time.